All right.
Okay, I guess then we'll welcome back everyone. We're going to hear from Ben Chandran at the University of New Hampshire, who's going to tell us about solar wind acceleration and coronal heating. And I will monitor your chat, Ben, and do as we talked about. Take it away.
Great, thank you very much. It's a pleasure to be back here at the summer school. Wish we were all in person, but hopefully we'll make the most of this virtual session and also the office hours later this afternoon. So yes, today I'll talk about solar wind acceleration and coronal heating. And my presentation will have three parts. I'll begin with some background on the solar wind and the origin of the solar wind. I'll then turn to a discussion of one of the mechanisms that's believed to play an important role in powering the solar wind. And this is reflection-driven Alfvén wave turbulence. And that's something I'll define later and explain a little bit more later on. And then in the third part of the talk, I'll present an approximate analytic solution to two coupled problems: solar wind acceleration on the one hand and the heating of the corona on the other. And my focus in this presentation is really on trying to derive analytic formulas and present intuitive explanations for three quantities: the solar mass loss rate, m dot, the asymptotic wind speed, that's the wind speed very far from the sun, and also the temperature of the corona, and try to build up our understanding of this system through an analytic treatment. All right, so to begin with some background, as most of you are very familiar with, the solar wind is a quasi-steady, quasi-radial outflow of plasma from the sun. Near the Earth, some of its properties are listed here in this diagram. The outflow speed, denoted by capital U, ranges from 300 to 800 kilometers per second. The temperature is on the order of 10 to the 5 Kelvin, and the particle densities are several particles per cubic centimeter, typically. The rate at which the sun loses mass, m dot, is approximately 10 to the minus 14 solar masses per year. And the total solar wind power, or mechanical luminosity, is 10 to the minus 6 times the sun's radiative luminosity, indicating that the solar wind is not a huge part of the sun's energy budget. It's a small part of the sun's total energy budget. Nevertheless, it's a very interesting object of study for a few reasons. It's a theater for all of space physics and space weather. It's a model for other astrophysical outflows, and also a laboratory for learning about fundamental plasma physics. To get an understanding for the solar wind in its own context, it is useful to begin by looking inward to the source of the solar wind, namely the sun, and even to the center of the sun's interior, which is shown with this cutaway figure here. At the center of the sun, in the inner part of the sun, is the solar core, the core of the sun, where the temperature is over 10 to the 7 Kelvin. The density is very large. The temperature is high enough that nuclear fusion reactions can occur. And those, of course, are the ultimate source of the energy of this system. In the inner 2/3 of the solar interior by radius, the primary mechanism for energy to diffuse outward to the surface is radiative diffusion, the diffusion of photons. But in the outer third by radius of the solar interior, the primary mechanism for energy diffusion is convection. That outer part of the solar interior, the convection zone, is convectively unstable. It's in a continuous state of turbulent motion. And that motion granulates the surface of the sun. You can see that granulation in this picture on the surface of the sun. And that is resulting from these continual turbulent motions that have typical velocities of order 1 kilometer a second at the solar surface. The surface of the sun is also referred to as the photosphere. That's the surface from which photons actually escape into space. That's the surface we see when we look at the sun, if you're unwise enough to look at the sun. And that surface divides the interior from the solar atmosphere. The lowest layer of the solar atmosphere is the chromosphere, and it's only a couple thousand kilometers thick. By comparison, the solar radius is approximately 700,000 kilometers. So the chromosphere is a narrow atmospheric layer, a thin atmospheric layer. On top of the chromosphere is the corona, which extends out a few solar radii from the sun. And the solar wind is really the expansion of the corona into the interplanetary medium. This slide here shows you the distance scale for this system. So lowercase r is the heliocentric distance. And here, can you see my cursor, by the way? It's pretty small, but can you see it around the R sun?
Yes.
I see it.
Yes.
Great. So that's the symbol for the solar radius, approximately 700,000 kilometers. And outside the solar interior, the solar wind is gradually accelerating up to those large velocities that I quoted earlier, 300 to 800 kilometers a second near Earth. It starts slow, but it gets faster. And there are a couple important transition points in the flow. The first is the sonic critical point, or just the critical point. That's typically a few solar radii out from the sun. It's where the outflow speed, capital U, equals the sound speed, the local sound speed. And inside of that radius, to the left of it, the flow is subsonic. To the right, the flow is supersonic. A little further out, about 10 solar radii out from the sun, you have the so-called Alphane critical point. That's where the local flow speed equals the local Alphane speed. The Alphane speed is the speed at which Alphane waves propagate. I'll define it and talk about Alphane waves a bit more later on in this talk. Another term I will use later on is the Subalphanic region. That's a region out to this Alphane critical point. So it's basically everything inside between the sun's surface and 10 solar radii out approximately. In that region, the flow speed, capital U, is less than the Alphane speed. Outside here, the flow is super Alphanic. Further out, you have the Earth sitting at approximately 215 solar radii, or 1 AU for astronomical unit. Pluto at approximately 40 AU. The solar wind, as it encounters the interstellar medium, it forms a shock called the heliospheric termination shock, and that sits at approximately 80 astronomical units. Much further out still is the next nearest star, Proxima Centauri, for about 300,000 AU from us. The temperature of this system is shown in this plot here. As I mentioned before, the core of the sun is very hot, above 10 to the 7 Kelvin. The temperature in the solar interior drops to about 5,800 Kelvin at the solar surface. The chromosphere ranges from several thousand to maybe 10,000 Kelvin. And then the temperature jumps up by a factor of about 100 to the coronal temperature of about 1,000,000 Kelvin. And it stays at approximately 1,000,000 Kelvin out to the Alphane critical point, beyond which the temperature starts to fall as a power law, approximately in radius, before ticking up again in the outer heliosphere. And one of our goals here is to explain this temperature profile and also the flow speed profile of this system. The density profile. Let's get the mass loss rate as well as we're going. So there have been a number of attempts to explain this system, and the most famous was the first, which was Parker's model in 1958 for the solar wind, and that was not so much an attempt to explain the solar wind. The solar wind had not yet been discovered. This was a prediction of the existence of the solar wind. It was very controversial. At first, somewhat famously, when Parker submitted this paper for publication to the Astrophysical Journal, the referees rejected it. And it was only through the intervention of the editor, Chandran, that the paper got published in 1958. And then a few years later, the solar wind was discovered, and it was a great triumph for Parker and the birth of the study of the solar wind. A number of other authors carried out similar studies as Parker. And so what I'm saying on this slide refers to actually several studies between Parker's first study in 1958 and work by, for example, Durney in 1970 or 71 and others. In these models that were developed early on, the following assumptions were made. The models took the system to be spherically symmetric in steady state. They neglected the rotation of the sun, which doesn't play a big role in generating the solar wind. Also, these models imposed a hot coronal temperature as an inner boundary condition, temperature on the order of the 10 to the 6 Kelvin that was observed later on. The wind is heated by conduction in these models and accelerated by the pressure gradient. And the model succeeded in explaining a supersonic wind. In fact, it predicted it before it was discovered, as I mentioned. But it also had a couple shortcomings. It wasn't able to explain those large solar wind speeds that I quoted to you early on, of order 800 kilometers a second, that are often observed at a heliocentric distance of 1 AU from the sun, particularly when you get out of the ecliptic plane of the planet's orbits around the sun. Also, the model did not offer an explanation for why the corona is so hot. That hot coronal boundary condition, that inner boundary condition, is critical for this model, but it's not really explained. It isn't explained in this model. A conclusion that was reached by Parker as well as others coming out of these early models is that near the sun, the dominant energy flux in the solar wind is not a heat flux, but something else, something that heats the corona and also powers the outflow up to those very rapid speeds. And an open problem that has been a focus of the community for the last several decades is what is this dominant energy flux and how is it converted into the kinetic energy of the outflowing solar wind? This problem is at the heart of a recent NASA mission, the Parker Solar Probe. The Parker Solar Probe spacecraft is shown here in this picture on the left, just prior to launch, which occurred in 2018. The really interesting, well, there are many interesting things, but maybe the most interesting thing about this mission is the orbit of the spacecraft, which is illustrated here on the right. Before this spacecraft was launched, the closest any spacecraft had gotten to the sun was 60 solar radii. The Parker Solar Probe, through a series of Venus flybys, is gradually adjusting its perihelion, distance of closest approach to the sun, which is eventually going to reach distances less than 10 solar radii from the sun's center. It's already gotten to within 16 or so solar radii of the sun's center. And so this mission is going to provide us with direct in situ measurements of the solar wind acceleration region and really help move forward this long, decades-old problem of trying to trace the flow of energy that heats and accelerates the corona and solar wind. All right, that's all I want to say by way of introduction. Let me now move on to the second part of the talk. One of the mechanisms and ideas that is believed, well, one of the mechanisms that is believed to carry a lot of the energy flux that powers the solar wind, an idea that will be tested by the Parker Solar Probe. This mechanism is reflection-driven Alfvén wave turbulence. To explain what this is, let me start with a basic idea. Actually, let me just quit my mail program so I don't keep hearing incoming mail. Sorry about that. And go back to full screen. So I'll start with a theoretical model for waves and plasmas. The one I'm going to use is ideal magnetohydrodynamics, or MHD. Three of the equations of an ideal MHD are shown here in this slide. The variables are rho, the density, v, the velocity, b, the magnetic field, and p, the pressure. That top equation is the continuity equation, which expresses conservation of mass. The second equation is the momentum equation, which is basically Newton's second law for a plasma. If you look at the form of the left-hand side of that equation, there's a mass density. And then this term in parentheses looks a bit like an acceleration, right? It's a time derivative of a velocity plus some extra term. It's actually the acceleration of a plasma parcel as it moves. If you follow the parcel and ask how does its velocity change in time, that is the quantity in the parentheses here. It's the convective derivative of the velocity. The left-hand side here is basically acceleration times mass per unit volume. So the right-hand side is going to be force per unit volume. And you have two types of force densities appearing, some from the pressure, some from the magnetic field. The third equation is the induction equation. It's basically Ohm's law for a perfectly conducting moving plasma. You close these equations with an energy equation. The appropriate choice for the energy equation depends on the application. There are 2 points I want to highlight about these equations. The first is a consequence of that third equation. It's the frozen-in law, which states that the magnetic field lines in a perfectly conducting plasma are like threads that are frozen to the plasma and advected at the plasma velocity, which is a phenomenally useful law for understanding how magnetic field lines or magnetic fields evolve in a plasma with flow. The other point I want to make has to do with the nature of the magnetic forces on the right-hand side of that second equation. So if you look at the terms containing B, we have this B squared over 8 pi term. That's called the magnetic pressure. And it appears in this equation in exactly the same way as the plasma pressure P. And that implies that the magnetic pressure exerts a force on the plasma in exactly the same way that the thermal pressure does. And the thermal pressure pushes from high pressure towards low pressure. The magnetic pressure pushes on the plasma from regions of high magnetic pressure towards regions of low magnetic pressure. That other term, the last term on the second equation on the right-hand side, the B dot grad B over 4 pi term, that's the magnetic tension term. And that's a force, the magnetic tension force, that arises when the magnetic field lines are curved. And it gives a force that acts to straighten out the magnetic field lines. If you put together the frozen-in law with the idea of magnetic tension, you immediately arrive at the physical basis of the Alfvén wave. which is illustrated in this slide. So you can understand this by considering an initial magnetic field line illustrated in black here on the left in some perfectly conducting plasma. And imagine you now displace the plasma along these purple lines. Because of the frozen-in law, those displacements drag the magnetic field line into a new shape illustrated with this squiggly line on the right, the black line. But then the magnetic tension force arises and it pushes on the field line in the direction of these green arrows, which acts to straighten out the magnetic field line. In fact, the field line straightens out and it then keeps going and then straightens out the other way. The whole field line oscillates. This is exactly the same physics as in a wave on a string. And the Alfvén wave is basically a wave on a string where the role of the string is played by the magnetic field lines. The Alfvén speed that I mentioned earlier, VA, is just the strength of the background magnetic field, B naught, divided by the square root of 4 pi rho, where rho again is the mass density. All right, so how do these Alfvén waves affect the origin of the solar wind? One of the leading ideas for the solar wind's origin is illustrated in the diagram on this page. It's a 4-step process. The first step goes back to those convective motions I mentioned earlier in the talk. Those convective turbulent motions at the surface of the sun are continually shaking the magnetic field lines that connect the solar surface to the distant interplanetary medium. That shaking launches these waves on a string, these Alfvén waves that propagate along these magnetic field lines out into the interplanetary medium. And the waves carry energy. So as they propagate, they're transporting energy away from the sun. They carry an energy flux. That energy flux can be very big in the solar wind. It can be the dominant energy flux in the solar wind, it turns out. The second part of this scenario is that those waves undergo partial reflection because of the radial variations in the Alfvén speed. Now, if this was a uniform plasma, uniform density, uniform magnetic field, the waves would just propagate in one direction without reflecting. But because of that variation in the density and magnetic field with radius, the Alfvén speed varies with position. That causes some of the Alfvén waves to reflect and go back towards the sun. The third step in this picture is that counterpropagating waves interact and become turbulent. So the outward propagating waves that the sun launches interact with some of the reflected waves. That causes turbulence. That causes energy to cascade from long wavelength waves to short wavelength waves. So that word cascade, it's a very important word in turbulence and in plasmas, which are often turbulent in nature. So cascade, energy cascade, is the transfer of energy from one scale length to another. So think about hydrodynamic turbulence. Take a big container of water, stir a big eddy in it with an oar. You'll generate this big eddy that will then later on break up into smaller eddies. Those smaller eddies will in turn break up into even smaller eddies and so on. When eddies break up into smaller eddies, they're passing their energy onto smaller scale structure. That's a transfer of energy between scales. That's an energy cascade. And it goes from large wavelengths or large scales to small wavelengths or small scales. Now, eventually, whether it's hydrodynamic turbulence or this Alfvén wave turbulence, at sufficiently small scales, the waves dissipate. And I will just say, in the case of Alfvén wave turbulence, the object that's breaking up is not a hydrodynamic eddy, but it's an Alfvén wave packet that breaks up into smaller wave packets and smaller wave packets. But eventually, it's small enough wavelengths, they'll reach wavelengths of order the proton gyroradius, and there are all kinds of things that can dissipate the Alfvén waves at those short wavelengths. And so the waves dissipate, and that heats the plasma. That's the fourth part of this scenario. And that heating increases the thermal pressure, and then the thermal pressure, along with the wave pressure, accelerate the wind away from the sun. So a couple questions immediately arise about this scenario. The first is, why invoke turbulence? Why can't we just have waves propagate away from the sun and then you get your coronal heating and your solar wind? The reason is that in the absence of turbulence, these waves that are launched by the sun, they're at comparatively large wavelengths and they're virtually undamped. They would propagate all the way to the Earth with minimal damping. And so they would not transfer any of their energy to the plasma through heating, and you would not be able to explain coronal heating. A second question that arises is, why invoke reflection? Why not just have the waves go out, become turbulent, heat the plasma, and then you're done? Why do we need this reflection? It turns out that one of the most vigorous ways for generating Alfvén wave turbulence is through the nonlinear interaction of counterpropagating waves. The reflection provides the inward propagating waves that you need for a mix of counterpropagating waves. So they're very important in this scenario. I want to talk about a couple of the key physical ideas that underlie this picture here. And the first of them has to do with how the waves would behave in the absence of dissipation. So forget the turbulence for a moment. Just imagine the waves were propagating away from the sun. What would happen to their amplitudes as they moved from the low solar atmosphere, where the density is very high, out into the solar wind? Well, in this limit, when there's no dissipation and also no reflection, I'm interested first in thinking about the case where there's neither reflection nor dissipation. We can recover this limit through the so-called WKB limit, the short wavelength limit. And in this limit, there's a conserved quantity called the wave action. The wave action is analogous to the adiabatic invariant of an oscillator. For example, the magnetic moment of a particle gyrating in a magnetic field, or the adiabatic invariant of a pendulum. It's basically energy over frequency. And an Alfvén wave in a plasma is like a whole bunch of oscillators. It's like a continuum of oscillators. And if you compute the energy divided by frequency for this wave field, you get the wave action. And its conservation causes this quantity at the top of the screen to become constant, invariant with radius. This quantity y is the ratio of the local density to the density at that Alfvén critical point, about 10 solar radii from the sun, all raised to the 1/2 power. Z plus is used to denote twice the RMS velocity of the outward propagating Alfvén waves. It's just conventional notation. It's like the wave amplitude. This equation of wave action conservation has two interesting limits. So first, close to the sun, the density is much bigger than it is out at the Alfvén critical point. The density drops very rapidly with radius as you go away from the sun. And so y is very large, and that equation at the top of the screen simplifies to a simpler equation. Y times z plus squared is a constant. Well, that leads to the following scaling. Z plus goes like y to the -1/2 or rho to the -1/4 power. That means as the waves move away from the sun into a lower density plasma in this region, their amplitudes go up. One way of understanding that is the following. In this region close to the sun, inside the Alfvén critical point, the Alfvén speed is bigger than the flow speed. To an approximation, you can forget that the plasma is even moving. The Alfvén waves are just like whipping through a very slowly moving plasma. And you can just treat the plasma as basically stationary. And the physics is then similar to the physics of a whip cracking. So if you imagine a wave propagating along a string, but now your string is a whip, it's a tapered whip. If you have a pulse moving along your string and the mass per unit length is getting smaller as you go, the amplitude of the oscillation is going to go up to conserve energy. And that's what happens in this system. So it's this whip cracking effect. Further out from the sun, beyond the Alfvén critical point, you have the opposite limit, that the density is smaller than it is at the Alfvén critical point. Y is small. That equation at the top becomes approximately z plus squared over y is a constant. That means that z plus is proportional to y to the 1/2 power or rho to the 1/4 power. Out there, the wave amplitude goes down as the waves propagate into lower density regions. And the reason for that is in that limit, beyond the Alfvén critical point, the wave speed is smaller than the flow speed. You can almost forget that the waves are even propagating. They're stuck to this expanding flow. Because of that, as the flow expands, the waves do work, pressure work on the plasma. They lose energy as they do that work. That causes their amplitudes to decrease. It's like adiabatic cooling. So that second to last point there ends up being really critical for the solar wind because it leads to strong extended turbulent heating out to the Alfvén critical point because that whip cracking effect keeps the wave amplitudes high all the way out to 10 solar radii from the sun. So that leads directly into the first of two key modeling results that I want to share with you about Alfvén wave turbulence in the solar wind. And it's a result from a paper that I just published in the Journal of Plasma Physics, which I'll also refer to again a little later in this talk. And you can show analytically, I won't go through the details here, but you can see them in this paper, that heating by reflection-driven Alfvén wave turbulence generically causes this subalphanic region out to 10 solar radii to become approximately isothermal, but not the region outside the Alfvén critical point. That region is not isothermal. This result is actually sort of already known, and it's illustrated by this is one example, but many solar wind models which find this to be the case. So this is a model from a paper by Verdini et al. of an Alfvén wave-driven solar wind. And you see in this model, several different model curves are plotted with these lines, and here are some data points that they compare to. The variation in the temperature between 1 and 10 solar radii is a factor of 2 or 3. On the other hand, the variation in the density over that same region is a factor of 10 to the 5. That's what I mean by approximately isothermal. It's not truly isothermal, but it's almost isothermal in the sense that if you had an adiabatic plasma that was with an adiabatic index of 5/3, if this plasma's density dropped by a factor of 10 to the 5, then the temperature would change by orders of magnitude. And here we don't see that. It's only a factor of 2 or 3. So it's almost isothermal. The other modeling result I want to share with you is that between 50 and 70% of the outward propagating Alfvén wave power at the coronal base dissipates before it reaches the Alfvén critical point. So the majority of the power in the Alfvén waves at the coronal base goes into heating the subalphanic region. All right. That's all I want to say about this reflection-driven Alfvén wave turbulence. Let me now get to the heart of the talk. An approximate analytic solution to the coupled problems of coronal heating and solar wind acceleration. So I just got done saying that the subalphanic region is approximately isothermal. So let's see if we can get an approximate solar wind model by treating the solar wind out to the Alfvén critical point, at least, as isothermal. Well, this has been done actually some time ago, and this is one example of this. Other authors have also looked at this. And I'm going to run through this calculation because it also illustrates key physics about the Parker model. And this is a very good thing to have a good grasp on if you want to understand the solar wind and key ideas in solar wind physics. So let me go through these equations, even if quickly. The first equation here is just the momentum equation divided by the mass density in spherical coordinates. In that you can just work this out yourself from the equation I quoted earlier. This is the pressure term. This here is the gravitational force term. The second equation here states the following. M dot is the rate at which mass flows through a sphere of radius r centered on the sun. And that rate is just the area of the sphere, 4 pi r squared, times the mass flux, which is u times rho. And that is independent of r in steady state. You take the derivative of this, and then you divide by m dot, and you arrive at this equation 2. This is basically just the continuity equation of mass conservation for this spherically symmetric system. You can use this equation 2 to eliminate the velocity derivative in equation 1 and replace it with a term involving the density derivative. So if you do that, eliminate du dr in equation 1 in favor of d rho dr, you get equation 3. Where you collect all the d rho dr terms on the left and all the other terms on the right. Equation 3 is very interesting. In our transonic solar wind, that means a solar wind that's subsonic, close to the sun, supersonic, far from the sun. This factor in parentheses on the left changes from positive, near the sun, to negative, far from the sun. So it passes through 0. If we want a smooth solution, where d rho dr is finite everywhere, at the location where the quantity in parentheses is 0, the right-hand side of that equation must also be 0. That location is the critical point, the sonic critical point at radius r sub c. And at that point, the flow velocity, denoted u sub c, equals the sound speed, which in this model is isothermal, so it's constant. And the condition that the right hand vanishes gives us this second equation here on the right, a critical point condition. The fifth equation here is the Bernoulli integral for this system. It's simply obtained by integrating equation 1 over r, just term by term. And you get this equation, the sum of these 3 terms is a constant. You can evaluate that constant by evaluating the left-hand side at the coronal base, which I'll denote with a b subscript. So rho sub b is the density at the coronal base. The left-hand side of this equation, at the coronal base, you can drop the first 2 terms because the flow speed is much less than the escape velocity at the coronal base. At the coronal base, the radius is about the solar radius. So this third term here is very large compared to the first term. And then rho equals rho b at the coronal base. So the natural log of 1 is 0. So you get this constant of integration on the right-hand side. And then you can evaluate equation 5 at the critical point, where the density rho is rho sub c. You get equation 6. If you plug this expression for, or you exponentiate it, then plug the expression for rho c into the expression for the mass loss rate evaluated at the critical point, you get the mass loss rate, an analytic expression for the mass loss rate. And indeed, this is one of the goals I had for this presentation, is to find an analytic expression for the mass loss rate. But have we really achieved what we wanted? Let's think about this. A couple things about this calculation I want to highlight for you. So before I get to that last question as to whether we have succeeded yet, let me first comment on this critical point condition. It seems a little bit like a mathematical subtlety, like some kind of subtle mathematical point, not obvious right away what it corresponds to. It turns out it's actually a very, it's the mathematical encapsulation of a very simple physical idea. The critical point is not just the point where the flow speed equals the sound speed. It's also a point at which the plasma becomes gravitationally unbound. It's a point where the flow speed, sound speed, and also the local circular velocity are all comparable. Now, because the gravitational force decreases with radius from the sun, there's nothing that can prevent plasma at that critical point from continuing to expand ultimately at approximately the sound speed. It's just like if you had a container of gas in space at some temperature with some sound speed, and you instantaneously removed the container, the gas would expand into a vacuum. What would be the speed at which it expanded? It would be comparable to the sound speed. Something analogous happens at the critical point. There's nothing that can stop that plasma there from expanding at roughly the sound speed. And that's why you get this expression here in equation 7 for the mass loss rate. It's the local density times the local speed times the area of the surface of the sphere centered on the sun that passes through the critical point. All right. Now, second, as the sound speed decreases, the density scale height in the corona decreases. Like I'm getting at, why is this formula here exponentially sensitive to the sound speed in the model? And the reason is that as the sound speed decreases, the density scale height in the corona decreases. And that means that you have exponentially less density at the critical point, and that causes m dot to decrease exponentially. The final point I'll make is this, and it has to do with the question is, have we succeeded in our goal of getting an analytic solar wind model? This formula actually has very little predictive value for us unless we can determine the sound speed with exquisite accuracy. That's because tiny variations in CS lead to enormous variations in m dot because of this exponential sensitivity. Just as a note, observations tell us that CS is on the order of 1/6 the escape velocity from the sun. So this quantity here is something like exponential of -18 plus 3/2 here. That's a very large exponential reduction. If you may have small variations in CS, you'll get large variations in that exponential factor. So we have to do something more, and that leads me to the last part of this talk. Last part of this talk. And this is to try to go beyond this, to figure out what CS is, to basically do the coupled problems of coronal heating, which determines CS, and then also solar wind acceleration, which determines m dot and U infinity. I will only have time to go through the back of the envelope calculation version of this calculation, maybe a few minutes to talk about the more sophisticated analytic treatment. Both are contained in that same paper I mentioned earlier, and if you'd like to read more about this, I've also included some extra slides in this presentation, which will be made available to you, which you can look at for like the Reader's Digest introduction to this calculation. But let me first go through the back of the envelope steps, which really illustrate some of the key ideas behind the model and get us close to our ultimate goal. So the first step in this calculation is where we just left off, the Hansteen and Veli result for m dot in an isothermal wind. So the essential assumption in this model is that the solar wind is isothermal out to the alpha critical point. That's only approximately true, but this is an approximate model, so it's a useful thing to use. I've written this expression slightly differently. It appears that m dot is proportional to the alphane speed at the coronal base. Again, the B subscript indicates that the quantity is evaluated at the base of the corona. But that's actually a mirage because this constant C1 that I've defined contains a VA in the denominator. It's just another way of writing what I just wrote on the previous slide. All right, as I mentioned, we need to determine CS to close this, to figure out what m dot actually is. So a natural way to do that is to consider the internal energy balance of that isothermal subalphanic region. That's done here. So what I've done here is I have balanced the sources and sinks of internal energy in that region. The left-hand side here is the sink of internal energy, the dominant sink. That is pressure work. As the plasma is going out in this expanding wind, it's doing work and it loses internal energy through PDV work. Now, why is that the rate at which the plasma is losing energy, internal energy in the region? The reason is that every time the plasma density drops by a factor of E, you have to replenish its internal energy to keep it isothermal, to keep it at that isothermal CS that we were assuming. The number of E foldings of the density between the coronal base and the Alfvén critical point is the natural log of rho B over rho A. CS squared is about the internal energy per unit mass. So CS squared times this natural log is the heating cost per unit mass for plasma to transit the quasi-isothermal subalphanic region. Multiply that by m dot, which is the mass per unit time flowing through that region, and you get the heating cost per unit time to sustain that quasi-isothermal subalphanic region. As I mentioned earlier, there's that work by, I didn't mention the authors, Perez et al., Perez, myself, Mihailo Martinovic, and Chris Klein, in a paper also in Journal of Plasma Physics from 2021, showed using direct numerical simulations that most of the Alfvén wave power at the coronal base dissipates by the time it reaches the Alfvén critical point. So roughly at the back of the envelope level, the heating power of this region is approximately the Alfvén wave power at the coronal base. So this is another equation for CS squared, but it's not far enough because we have some more unknowns here, this ratio rho B over rho A. Let's fold in some more physics and see if we can close this set of equations. So let me define capital A to be the cross-sectional area of the flow. This is a function of heliocentric distance R. This ratio here is then independent of R. It's a constant in steady state. The numerator here is the mass loss rate through the flow area. That's mass flux times area. The denominator is the magnetic flux through this flow area. Each is separately constant. Their ratio is constant, cancel out an A. And then let's rewrite this in terms of the Alfvén speed, which before was defined as B over the square root of 4 pi rho. So that rho U over B is the same as rho to the 1/2 U over VA with, there's an extra constant square root of 4 pi in there, but I'm not worried about that. It's just some constant. That constant in this middle equation here must be the density at the Alfvén critical point to the 1/2 power. That's because at the Alfvén critical point, U equals VA. So we have this equation that allows us to replace the local flow velocity with the local Alfvén speed times a factor involving the density to the -1/2 power. We can use this to get another expression for the mass loss rate at the coronal base. It's just 4 pi r squared rho times U. Let's evaluate that at the coronal base. 4 pi r sun squared. R sun is about the same as the radius of the coronal base. The density at the coronal base. These last terms here are the flow speed at the coronal base. Alfvén speed times that density ratio to the 1/2 power. But notice now we have two expressions for the mass loss rate. They're in these green boxes. They must be equal to each other. In fact, their natural logs must be equal to each other. And that is the equation I've shown here. This log of C1 term is just a logarithmic correction. What this equation is really telling us at the back of the envelope level is that V escape squared and CS squared are related via this natural log term. Well, notice this nice quantity appearing on the right-hand side here. That's familiar. That's that heating cost per unit mass for plasma to transit the subalphanic region. So what we've learned is that in an Alfvén wave-driven solar wind, the heating cost per unit mass for plasma to transit this subalphanic region is just V escape squared. It's really astonishing that this combination of parameters is always given by V escape squared. Why is that? Well, one reason why this product here is constant is this answer is really only explaining why this product here is basically constant as a useful check. It's that increasing CS squared leads to an exponential increase in m dot, as I was discussing before, and therefore an exponential increase in the solar wind density out at the Alfvén critical point, and therefore an exponential reduction of rho B over rho A. And that leaves this product, CS squared times that natural log, approximately unchanged. All right, armed with this result, we're now in business. We now revisit that second equation for the energy balance And that quantity, well, we first rewrite that as m dot is the Alfvén wave power at the coronal base divided by that CS squared natural log of rho b over rho a term. But that denominator there is just the escape squared, the heating cost per unit mass to transit the subalphanic region. And this is the approximate formula for the mass loss rate of the sun that we're looking for. It's actually very simple, which is actually quite nice. Energy conservation then tells us the following, that the total solar wind power is independent of radius. Far from the sun, the total solar wind power is carried primarily by the kinetic energy of the solar wind. And out there, the solar wind power is just 1/2 m dot times u infinity squared. At the coronal base, the solar wind power is primarily in two forms. The first is the Alfvén wave power, and the second is a negative power, which is the gravitational energy flux times the area. It's basically the cost of raising the matter out of the sun's gravitational potential well. Now, in the previous equation, we have an equation that tells us that the Alfvén wave power is simply m dot times v escape squared. Plug that into this equation, the right-hand side becomes plus 1/2 m dot v escape squared. That equation tells us that u infinity is approximately the escape. This is also a very simple result, but also similar to what we see in the solar wind. The escape velocity is 617 kilometers per second. Interestingly, this reflection-driven solar wind turbulence is acting like a mirror in energy space. The energy per unit mass goes from minus v escape squared over 2 approximately near the solar surface to plus v escape squared over 2 far from the sun. Another couple lines, and I won't go through this because time is short, can give us the temperature calculation for the corona in terms of the RMS velocity of the Alfvén waves at the coronal base. That simple calculation is contained in the first few pages of that paper. It's just a couple of lines. Now, this is okay at the level of a back of the envelope calculation, but to do a better job and really compare to observations, we have to fold in additional physics. For example, one thing I haven't mentioned yet is that there's an important loss mechanism for energy in the corona and subalphanic solar wind, and that is the conduction of heat down through the transition region into the lower solar atmosphere. That heat gets conducted down and radiated away. That needs to be accounted for. Another important effect is that some of the Alfvén wave power survives beyond the Alfvén critical point where it keeps pushing on the plasma and accelerating it faster. That needs to be accounted for. Also, I haven't said anything about the Alfvén wave pressure force on the plasma. That also helps drive the outflow. That also needs to be accounted for. So to get a more refined calculation, what I did in this paper is develop a more sophisticated model based basically on the same assumption that the subalphanic region is isothermal. That's its first assumption here. I defined the coronal base to be the radius at which the local heating rate equals the radiative cooling rate. I can talk to you more about that in the office hours later this afternoon if you're interested. And for simplicity, I neglect radiative cooling above the coronal base, and I neglect turbulent heating below the coronal base, where in the transition region, where the heat conduction, the heating rate from the heat flux, divergence of the heat flux is much bigger than the turbulent heating rate. And it's that conductive heating that balances the radiative cooling in that dense transition region plasma. I will quickly whip through this to leave just a couple minutes for questions at the end, but we can do more questions in the office hours. So the main mathematical elements of this model are stated here. There's a simple turbulence model. So the decay length for the wave action flux, which would otherwise be in conserved quantity, the wave action, the decay length for it is twice the local density scale height divided by an adjustable parameter that I call sigma, which you can vary to reproduce different types of solar wind. There's an integrated continuity equation, integrated momentum equation, critical point conditions like the ones I mentioned to you earlier, then internal energy equations twice, once for the subalphanic region and once for the transition region. This yields 3 simultaneous transcendental equations in 3 unknowns, and I will quickly present a couple numerical solutions to these. And there's a slide here with a couple analytic solutions, which I'll mention just a couple more things about before I finish. let me show you quickly the internal energy balance of the subalphanic region. I will actually skip through this because I want to finish in just a couple minutes, but I'll show you the slides anyway. You can go through these at your leisure. And the other interesting thing about this model is that it includes the internal energy balance of the transition region, balancing local conductive heating against radiative cooling using the technique of Rosner et al. And Schwadron and McComas et al., slightly modified. You can get an analytic solution for the heat flux going from the coronal base down into the lower solar atmosphere that closes the model equations. And you can, with a couple plausible assumptions for the magnetic field strength profile, you can match, for example, Parker's solar probe observations by varying a single parameter. So really for any plausible choice of the magnetic field geometry encapsulated by the so-called superradial expansion factor at the coronal base, I could explain that more in office hours. You can vary this one parameter sigma and match these observations from the first perihelion encounter of the Parker solar probe. There are also analytic solutions in this paper for the mass loss rate and asymptotic wind speed that match the numerical solutions of those transcendental equations. And interestingly, that back of the envelope calculation that I presented to you is the leading order analytic solution in the so-called expansion dominated regime, where the primary loss mechanism of internal energy in the subalphanic region is pressure work. There's a lot more in the paper. Just very briefly, this may also be relevant to other types of astrophysical outflows, even relativistic outflows near black holes, even when there's space-time curvature. A lot of this physics of the Alfvén wave turbulence and heating carries over. I'll finish with my last slide here. The couple main things that I tried to convey today are that one of the main ideas for how the solar wind is generated is that the primary energy flux that powers the solar wind is carried by Alfvén waves, and they dissipate primarily through this reflection-driven turbulence, where some waves reflect, then counterpropagating waves interact, producing turbulence. In this type of turbulence, the wind is approximately isothermal out to the Alfvén critical point, and that lets you calculate the heating cost per unit mass to transit that region. And that heating cost is just the escape speed squared. That gives you an incredibly simple approximate back of the envelope formula for the mass loss rate of the sun and also the asymptotic wind speed. Higher order corrections to these formulas can be computed in this model analytically, accounting for effects such as the wave momentum deposition, conductive losses, and also the survival of Alfvén wave power out to large distances. And this is an incredibly exciting time for studying this physics, both because of Parker Solar Probe, but also because of Solar Orbiter, a mission launched by the European Space Agency, which was launched in 2020 and is already taking data and is a beautifully complementary mission to the Parker Solar Probe. And this is going to be an exciting decade where we learn what we learn not just about the solar wind, but for also what we learn about how the solar wind informs our understanding of other astrophysical outflows. Thank you for your attention.
Thank you, Ben. Very, very nice analytic description. I think we have now a few minutes for questions before we break. And then as he mentioned, Ben will be available during the office hour if you have more questions for him, longer format questions. A few people in chat thanking you. Okay. Well, then, I believe, thank you, Ben, again. And I believe we'll take a 10-minute break and then rejoin at 20 past the hour for Joe Giacalone's talk on cosmic rays, cycles in cosmic rays. And you're welcome to hang around or just rejoin us, Ben, when office hours start, which is at, make sure I get these all correct, 10 past 1 Mountain Time. So okay. That's, you can do that. Okay.
All right. See you soon.
Okay, thank you
Thank you,
again.
Ben.
I have my phone next to me as well.
Oh, yeah. Okay, well then, I think everyone should be back. Welcome back from your break. We've got a high energy end of the solar wind. This is the high energy charged particles in the heliosphere. And Professor Joe Giacalone is going to talk about it, joining us from the slightly warm city of Tucson, Arizona.
Right.
I'll let you take it away, Joe.
Thank you, Dana. Okay, well, welcome to you all. I really wish this could be in person. I would love to be in Boulder. I'm assuming that's where it would have been held, which would be presumably quite a bit cooler than it is here in Tucson. But okay, yeah. So as I was just sort of saying at the end, just to sort of reiterate something, I do have probably more slides than warranted for a 50-minute lecture. So please stop me any time you want. I don't have to get through all of this material. So please stop anytime you have any question about anything. But this talk, I've given a version of this before 8 years ago at the summer school. And that was 2 lectures at that time. So I've tried to condense this down a bit. So I can, so I've added some material that please look at your own time. But also I'll have office hours tomorrow if you want to go over any of that sort of stuff. So, okay, so let me just give a little motivation here. So high energy charged particles in the solar system this is basically a sort of classic problem. I heard Professor Chandran talking about Parker's contributions to space plasma physics in the past. I dare say he's probably the father of the field. He also did a lot of work on high energy charged particles. So, and I actually am, I would say, an academic grandchild of Parker, because his postdoc was Randy Giacalone, who was my mentor when I first arrived at Arizona. So I'm at least, and I was a postdoc under Giacalone. So through the postdoc ranks, I'm an academic grandchild of Parker, and I tend to present things from his way of thinking. But this is a classic problem, and he worked on it quite a bit. He has a very famous paper in 1965 he wrote, which I'll talk about in a little bit. But just more generally, this problem stretches across fields. It's not just a heliophysics field, it's also in astrophysics. The highest energy cosmic rays well, not the highest of highest energy cosmic rays, but cosmic rays, the bulk of cosmic rays are thought to come from supernova remnants. The physics of that we can study mostly, well, only right now remotely. Of course, those remote observations are getting to be quite revealing, but the heliophysics offers a really sort of unique way to study the basic physics of this problem. And while the sun and the heliosphere don't produce energies that we see at supernova remnants, the basic physics is similar. The other thing I would add is that I've been in the field. I got my PhD in 1991, and I have been working on aspects of particle acceleration most of my career. So the message is that there's many unsolved problems. Heliosphere provides numerous in situ observations. One can build an entire career out of this field. And it's a small niche of heliophysics, as you're finding in summer school. There's in this summer school all these different areas of study. But even within this small sub branch of that, there's numerous of problems to work on. There's no end of questions in this field. So we do have pictures. I'll show in a second a picture of high energy charged particles, but generally we don't have pictures of high energy charged particles. So the way we represent them is through a distribution function, or in this case, something known as the differential intensity. It's related to the distribution function. It's actually p squared times f. F is the distribution and p is the momentum, also known as the flux. So this is the flux versus energy. And this is the way energetic particle people typically represent energetic particles.
Joe, I'm only seeing your introduction slide, so.
I have a feeling. Let me stop share for just a second and share again.
Sorry about that.
No, that's quite all right. Quite all right. I think that when the recording started, it kind of took me out. Something about that, right? So are you seeing anything right now?
Yeah, I can see that. You're still in presenter mode.
Okay.
Yeah, there's, right, if you hit that, should we go into slideshow? Yeah, okay.
And now I'm on, so that was the motivation slide,
Okay, there's the motivation slide.
which everybody missed, but I'm not going to do it again.
Yeah.
Okay. It's just pictures. Okay. And then this is the slide I was just talking about. So thank you for catching me. I didn't want to get too far along. But hopefully people see a distribution here. Okay. With some, so this distribution reveals a few things that I want to point out. So, and this is sort of an inventory of energetic particles that are in our heliosphere, even though this particular spectrum that's being shown here is taken at 1 AU. It's data from the ACE spacecraft, which sits out at L1, about 1/100th of an AU towards the sun from the Earth. But in blue is a sort of composite sort of spectrum over about almost a 3-year period. You see the solar wind part of the distribution at low energies where the spectrum sort of rolls over. And actually there's the solar wind has both a slow and high speed component, a slow and fast. It's almost bimodal, but on this kind of distribution, you see it's kind of a smoothly between the two. But then you see this high energy tail. So this high energy tail here is what this lecture is about. And this high energy tail, when you add it up over 3 years, has a lot of different parts to it. One of it is these galactic cosmic rays, which is this bump way out here. These particles come from outside the solar system. And at 1 AU, they are modulated. So we don't see, there are cosmic rays of these energies, but you have to be in interstellar space to see them. The heliosphere shields the low energy galactic cosmic rays from coming in. So this little tail out here is the modulated part. And at 1 AU is very, for a galactic cosmic ray, reaching 1 AU is kind of difficult, okay? Because it's if you look at a picture of the heliosphere, 1 AU is usually about the size of the sun on those images. Okay, there's also something known as anomalous cosmic rays, which I'll discuss in just a second. These are actually cosmic rays. Okay, they're not rays, but they're high energy charged particles that are accelerated in the outer heliosphere and propagate back into the Earth. That's this little black dash line here. And then there's solar energetic particles. In the semantics, solar energetic particle is actually a sort of general term, and there's a lot of different components to it. On the one hand, when you have a very large event, say mostly associated with a coronal mass ejection or a very large flare. Often when you have a very large X-class flare, you almost always have a CME as well. And at 1 AU, you often see a very large particle event, which is called gradual because it's sort of depending on how you're viewing it. Sometimes you see a slow rise, but then it lasts for a very long time. Okay, it's not a quick burst. So the largest of all of the events that we see are typically called gradual solar energetic particle events. Then there's more frequent, lower intensity, very short-lived events that are associated with impulsive solar flares. These are smaller type solar flares, not the X-class ones, but the C-class flares and less. Those are both solar energetic particles, but they're different types of solar energetic particles, okay? Then there's solar energetic particles associated with coronal mass, co-rotating interaction regions. I don't know whether you've had a chance to learn about CIRs. I don't want to get into that too much, but basically it is a interaction region formed by the dichotomy, the fact that you have the high speed solar wind in sort of coronal hole regions and low speed solar wind in the equatorial regions of the sun. And because that symmetry is actually aligned with the solar magnetic axis and not the rotation axis. As a result of that, you have these places where high-speed solar wind is overtaking slow-speed solar wind, creating these co-rotating interaction regions. These are very well known producers of energetic particles, and that's been studied for quite some time. Those are also SEPs, but a different type of SEP. And then unfortunately, that it's the same set of letters, SEP, but in a slightly different order. SPE is something known as a solar proton event. These are actually, it's basically when NOAA goes, that particular set of spacecraft, there's a bunch of those spacecraft, but when NOAA sees an event that has certain characteristics, it's above 10 MeV, there's more than 10 particle flux units, particles per square centimeter per second. Above that energy, then it's classified as an SPE. These are among the largest events that we see. Not every SEP is an SPE, okay? And then the most extreme events of all that we see from the sun that are the class of SEPs are these so-called ground level enhancements. These are events that reach such high energies with such high intensity that they can actually be seen on the ground through neutron monitor detection, which is the way we observe, one of the ways we observe galactic cosmic rays. The other is air showers. To my knowledge, ground level enhancements don't produce air showers, but I don't quote me on that. Actually, I'm being recorded right now, so maybe my experts are probably going to come back and give me a hard time about that. There's also energetic particles from magnetospheres, but that's not what I'll be talking about in this lecture. This is a well-known plot that shows the anti-correlation between the number of sunspots on the sun, the average sunspot number, and cosmic ray flux. The bottom panel is actually counts of neutrons. This is a neutron monitor in Antarctica from McMurdo Station. Neutrons are one of the byproducts of the nuclear interaction when a high energy galactic cosmic ray proton strikes our atmosphere and produces a cascade of basically an air shower coming down. But one of the products is neutrons that reach the ground and are counted through many neutron monitors that we have. And we see this well-known anti-correlation between sunspot number and cosmic ray flux. You also might notice that there's in addition to the 11-year sunspot cycle, there's also a 22-year cosmic ray cycle. You see this is, well, let's take this one, is a triangular shaped pattern here and here, and it's more flat top here and here. Unfortunately, I don't have the latest plot of this, but it's triangular shaped here, flat again, and so on. So there is a 22-year cosmic ray cycle in addition to the 11-year cycle as well. And by the way, this well-known anti-correlation between sunspot number and cosmic ray flux is actually used in sort of long-term proxy records using, say, C14 data, or looking at ice cores, beryllium-10, and other of these long-term records that we can determine sort of the cosmic ray flux, and through this correlation here, solar activity going back many thousands of years. It's this sort of well-known correlation that gets utilized in that. Very recently, the last couple solar minimum have been so deep and so profound and so few sunspots that the cosmic ray flux, in fact, have reached all-time records. I believe that I think depending on which station observes it, I believe there was a record of a cosmic ray flux being even higher this last minimum than the one that occurred in 2009, 2010. But again, not every neutron monitor has detected this. But to suffice it to say, the last two solar minima have been quite substantial in the amount of cosmic rays that are arriving at the Earth. And in fact, I should point out, even during the last solar maximum, the cosmic ray flux didn't even go down very deeply. I mean, you could see the amount that it went down during the previous solar maximum were far more than this last one. So we have entered a period where there's been a lot more galactic cosmic rays, over extended periods of time, which is probably not very good for space travel. If you want to get to Mars, you probably want to go during a period when there's a lot of solar activity, so you have to deal with solar energetic particles. But the galactic cosmic rays, which are probably the ones that are of most concern, you might want to go when that's low. As I mentioned, the heliosphere plays a critical role in this. I don't want to spend too much time on this. Hopefully you've seen a picture of the heliosphere. But in particular, one aspect of the heliosphere I want to highlight right now is this termination shock of the solar wind. So I'm assuming Professor Ofer went over this, but just to say the relevant bit that I want to talk about right here, because I'm about to transition to something called anomalous cosmic rays. In addition, galactic cosmic rays have to move through this entire thing to get to the Earth. And as I pointed out, Earth is just really way in here. The solar wind is supersonic, and that it's interacting with this medium outside, which is providing primarily a thermal pressure, but also some dynamic pressure that causes several boundaries. And one of these boundaries is the termination shock of the solar wind, where you're going from supersonic solar wind to subsonic solar wind, and then maybe even across the heliopause, where you go from solar wind to interstellar medium. Both of the Voyagers have crossed this boundary now. Both Voyagers are in interstellar space, just beyond the heliopause boundary. But anyways, this shock wave right here, this termination shock of the solar wind, is a very efficient particle accelerator and leads to a subset of cosmic rays that are known as anomalous cosmic rays. In terms of the spectrum plot that I've shown before, they're best represented. I like to show it this way. So first of all, the black is galactic cosmic ray protons. That's actually all particles, but it's mostly protons. You see this rollover, and that's the modulation that I was saying before. This is not what the spectrum looks like in interstellar space. It's what it looks like at 1 AU, because the heliosphere keeps out the low energy particles. It's best seen in oxygen, but you can see it in all these other species. Here is, for the case of oxygen, you see this modulation. So these are galactic cosmic rays, but you see this other little bump in the spectrum at lower than galactic cosmic ray energies. The energy happens to be about 100 MeV per nucleon, 100 MeV total energy. Okay, and interestingly enough, that energy, 100 MeV, happens to be the potential difference between the pole and the equator of the heliosphere. If you take the ideal MHD electric field, the U-cross-B electric field, and you ask from pole to equator, what is the potential difference associated with that electric field over that path length, it comes out to about this energy. So that's actually an interesting clue as to where they come from. And in fact, what the physics, what we think that they are they start out their lifetime as an interstellar neutral particle that makes their way into the heliosphere. They get ionized either through charge exchange with the solar wind, which is the most likely process, especially for protons and for oxygen as well, or through UV. Helium is an example. Helium makes it in quite close to the sun before it gets ionized, and that's primarily UV. Once it gets ionized, now that original neutral particle is what's called a pickup ion, and because of the way forces work on individual charged particles, they get there's an electric field drift that basically takes them out of the solar system. That electric field drift is along the same direction as the solar wind, and so they're called being picked up. That's why hence the name. But once they get out to the termination shock, they get accelerated. They are a suprathermal population, so they have a slight advantage over the solar wind in the acceleration process. And they get to the termination shock where they get accelerated. And the maximum energy attainable is when they drift the full length. The energy gain happens by drifting against the electric field, the motional electric field of the solar wind. And the maximum energy they can gain is when they drift all the way from pole to equator. And that maximum energy is roughly consistent with as I said, the potential difference. Well, that's great. That was the theory a long time ago. But then, of course, we have these in situ observations, which always throw a fly in the ointment or a wrench into the system. These are plots by Voyagers 1 and 2 showing energetic particles. So these are time intensity. So these are intensities at different energies. The red is Voyager 1, the blue is Voyager 2. Voyager 1 crossed the termination shock in late 2004. And that's indicated by that green vertical dashed line, whereas Voyager 2 crossed it a little bit later because it was trailing behind. Interestingly enough, little side note, Voyager 2 was actually launched before Voyager 1 by about a month, I think. But because of the celestial mechanics and the way they were going to go and visit the planets, Voyager 1 ended up being farther out than Voyager 2. But they have detectors that measure energetic particles, and one of them is LECP, Low Energy Charged Particle Experiment. Tom Cremegis is the PI, and Rob Decker, the PI of that instrument. And at the really lowest energy, so these are above solar wind energies, but just sort of where the tail starts in the distribution. So these are low energy energetic particles is what I would call them, but they're above this thermal solar wind. You can see the rise occurred right at the crossing of the termination shock, both at Voyager 1 and Voyager 2. But at the highest energies, and these are what would be called true anomalous cosmic rays. Being a theorist, I think these are all anomalous cosmic rays. It's a continuum process. You've got to accelerate particles from low energies to high energies. It might not all happen at the same place, but in terms of the semantics, I like to think of all of these as they're accelerated pickup ions, and that's what anomalous cosmic rays are. But from the observer point of view, they sort of put these into different boxes, and the true anomalous cosmic rays are the ones that at the high energy ones. And it made news when Voyager crossed the termination shock that we didn't see the anomalous cosmic rays at the shock, that the intensity kept rising way beyond the termination shock, both at Voyager 1 and Voyager 2. And so this presented a puzzle, but and this is still debated, by the way. This is, again, an area of which there's active research. My favorite picture of this, and this has also been done quantitatively, but I just like this picture that was put forth by Dave McComas and Nathan Schwadron, where this is the termination shock, is it that big black thick line on the inside right here? This is the termination shock. It was noted in a previous paper that I happen to be involved in, but it was Randy Giacalone that came up with this idea when he was thinking about raindrops, by the way, raindrops falling through the atmosphere. He realized that because of the way Bernoulli's principle works, that the shape of the raindrop is actually blunt shaped. It's not perfectly spherical. And theorists up to this time had always assumed the termination shock was spherically shaped. But because of the hydrodynamics of the problem, the shock is actually blunt shaped and not spherical. However, the Parker spiral magnetic field, I heard you all talking about Parker's 1958 paper. I don't know which one you were talking about, but if it's the solar wind paper, he also did the Parker spiral in that paper. That Parker spiral magnetic field is actually, it's wrapped in a spherical way, or I guess circle on this projection. And it's this morphology difference between the direction of the magnetic field and the shape of the shock. And in fact, if you follow the intersection point of one of those magnetic field lines and the shock, if you follow the intersection point with time, you'll see that it moves along the shock. That's just because of this morphology. And because it takes time to accelerate particles, the acceleration doesn't happen instantly. At low energies, it happens quickly, but at high energies, it takes time. It takes about a year to get to these high energies. And in that year, that intersection point has moved along the shock over to here. And so the high energy anomalous cosmic rays are most intense at the sides or the flanks of the heliosphere. And so I think that is, like, to me, the best explanation. So they fill in through transport. They fill in, and you don't quite see the maximum intensity until you're here. And that's because Voyager crossed in the nose region over this way. It'd be nice to have a spacecraft move off to the flanks so we can test this theory. So I don't know, maybe interstellar probe. I think I'm going to skip these 2 slides, but this is sort of some latest research.
So Joe, there's a question from Nina, and it's the decline in KeV to MeV particles in Voyager 1 after 2006. Is that believed to be a feature or just what Voyager 1 happened to measure?
So these are these things right here. Yeah. Yeah. Okay. Unfortunately, Voyager 1 does not have a functioning plasma instrument. And I don't have, okay. Cutting to the chase, I don't put either the magnetic field or the solar wind on these plots. And so I can't answer the question without just going to my memory. I don't believe during those periods there was anything in the magnetic field that indicated there being some structure there, but clearly these intensity variations have to be caused by something. The plasma instrument was unfortunately not functioning. It got knocked out when it went by Saturn, I believe. Voyager 2 does have a functioning plasma instrument, and I can only say that sometimes you do see variations in energetic particles that are clearly associated with variations in, say, plasma compressions or magnetic field. Like a glow, like because the solar wind, there's these large, like a CME continues. They can actually merge with preceding CMEs. By the time you get out to 100 AU, all of these things tend to merge together to form something called a global merged interaction region. And when those things make it into the heliosheath, this is now shocked solar wind, something known as the heliosheath. These GMERs can often produce features that are like this. I'm not going to say that that's what happened in this particular case without looking at the plasma data, but unfortunately the plasma data wasn't available. And my recollection of the magnetic field during this is that there was nothing obvious that produced that. But that's a good question. Yeah. Okay. So let me think. And by the way, I will just say I was moving on to this slide right here. Let me just say one thing. Let me just point out we have an instrument that measures anisotropies, and it was really quite interesting when we did cross the heliopause, for example. Let me just start with the 2 on the right, which are the easiest to absorb. The 2 on the right, the red and blue are just Voyager 1 and Voyager 2 shifted in time so that they supposedly crossed the heliopause at the same time. They didn't, so you have to shift the curves in time. But these are galactic cosmic rays in the top panel. So just to state simply, there's a lot of galactic cosmic ray modulation that takes place right at the heliopause. This is not that well understood. This is another active area of research. Why does the galactic cosmic rays change so dramatically very near the heliopause? Anomalous cosmic rays, on the other hand, leaked out. They just totally leaked out. They went essentially to zero. There's still a signal here, but that's just galactic cosmic rays leaking into the instrument, but at low energy. So the heliopause is a big sink. The anomalous cosmic rays leak out and go off into interstellar space. But the galactic cosmic rays, since we're finally at their source, there's a lot of modulation. There's a big change over the course of a year or so. And we do have these, let me just say it this way. We do have these instruments that can measure anisotropies. We can see which way they're going. And this is actually a really interesting area of research. But in this lower left panel, let me show it on the right in a different image. So this is now on the left. I think it's just Voyager 1. I believe it's just Voyager 1 that shows in the top plot, it's sort of the count rates of energetic particles. And I think it's all red is galactic cosmic rays, blue is anomalous cosmic rays. Again, you can see them go down. So the heliopause is way at the left. So almost this entire interval is in the interstellar medium. And there's not a lot happening with galactic cosmic rays. They're pretty level. But what is interesting is that we see this is now radio. So these are thought to be produced primarily through Langmuir waves at shock waves. And these Langmuir waves propagate a fair distance. And sometimes you see the Langmuir wave and you see a shock wave in the magnetic field. So this is the magnetic field, and you see the shock wave go up, and there were these Langmuir waves associated with it. But here's an event where you see these presumably Langmuir waves, but you don't necessarily see the shock because the spacecraft was not very well positioned to see the shock wave, but the Langmuir waves can propagate off a certain distance. And then here's one where you see the Langmuir waves well before, and then eventually you see the shock. But what's interesting in each of these, if you look at the anisotropies, this black curve right here are particles moving normal to the magnetic field, okay? And whereas the red is parallel to the magnetic field. So you see this interesting notch. So you all of a sudden start losing particles perpendicular to the magnetic field. And there's been quite a few papers about this recently. Jamie Rankin, now at Princeton University, she was a graduate student at Caltech and is now a postdoctoral research associate, or maybe even more promoted. I'm not sure. She works on lots of things, but she wrote a very nice paper on this. There's other people have noted this, but she had a sort of a nice summary of all of this, and it's related to the way disturbances propagate from inside the solar system through the heliopause and out, and how particles interact with magnetic fields, and magnetic mirroring plays a very key role. So I'm really just sort of highlighting this work without getting into too much detail. The other little puzzle I would like to mention is, well, yeah, it's again, there's been a couple of papers on this. I don't think it's a solved problem, but it's an interesting one. Forget about the black curve for now. The black curve is essentially the heliospheric current sheet tilt angle, but I haven't really talked about that yet. But the blue is galactic cosmic rays from neutron monitors. The red is anomalous cosmic rays from a spacecraft measurement. I believe it's ACE, Advanced Composition Explorer. But what is interesting is that, and again, here's that triangle-shaped flat top triangle shape again. But what is interesting is that the galactic cosmic rays were a lot higher at the last solar minimum than the one before it, but the anomalous cosmic rays were lower than the previous maximum. Okay, so it probably is saying something about the weaker sun's magnetic field produced a less efficient acceleration process at the termination shock. I think it's less of a transport process and more of an accelerate. It's telling you something about the efficiency of the acceleration. Okay, then there's sort of finishing my background, which is taking up most of the talk, which I suspected it would, by the way. The other thing is, in addition to the, this well-known galactic cosmic ray modulation, sort of this bottom, so this is now a plot of, I think this is, fairly high energy, energetic particles. But so you can see galactic cosmic rays, but in addition to that, you also see this sort of hair on top of it in a time intensity profile. So these are like roughly 10 MeV. I think it's CNO group ions. So oxygen, carbon, nitrogen. But what you see is both SEPs and galactic cosmic rays. So you can see these massive increases of solar energetic particles that at this particular energy range. At higher energies, you don't see it quite as dramatic as this. And solar energetic particles and their solar cycle dependence is actually quite interesting. Actually, the ACE and NASA, well, I guess this is GOES data. So we've got GOES data going back several or 3 solar cycles at least, and we've been able to measure the number of solar energetic particles. These are actually solar proton events. So these are the biggest ones. And if you just add them up as a function of solar cycle, you get this plot in the left, which is really quite interesting. So solar cycle 23, which is the one, so I think we're currently started in solar cycle 25 right now. So 24 was the most recent complete cycle, and 23 was the one before that. And that was a pretty large energetic particle producing event. And this is, again, just a sum as a function of days of solar cycle. You can see this sum is dominated by a lot of these large increases that you get, like big events, really, really big events. Like this is the famous Halloween storm period of 2003. And I think if you look here, this is the Bastille event. This was also a very big period here. So you get these big increases. But solar cycle 24 was really quite weak in terms of energetic particles. And there's been, again, a lot of studies trying to figure out why that is. It's not just the fact that the sun, the magnetic field is weaker, because the turbulence is also weaker, which is a key part to it. And so anyways, but there's other factors. I just wanted to point out the observation here, which to maybe motivate you to think about this, because it's not a solved problem, by the way. Okay, and then sort of this is my last slide of background. I want to, and all of the physics of all of this, we all basically use the same equations for galactic cosmic rays and for SEPs. But I want to talk about SEPs real quickly, and I like this observation as a sort of summary plot. What's shown here is a very typical, very large event. Okay, very, very large event. So this is a multi-instrument plot. It shows the high, and it's the lowest energies are at the top. So this is flux. So it's the lowest energies going down to the highest energies. You can see that the time intensity profile, so this is days on the bottom, depends on energy. So the highest energy particles get accelerated very rapidly. They come out to you and then they decay away with time, and you don't see too much when the CME actually crosses you later. So the event occurs at this arrow, West 23. So this was a Western Hemisphere of the Sun event, which is a well-connected magnetically because of the Parker spiral magnetic field. So the event occurred here. You see these high energy particles, but then when the shock comes by you, you don't see you don't see another jump at these energies. But at low energies, you don't see them early. This is all contamination, by the way. It's an instrumental effect. So this is all contamination. But the lowest energies you don't see until much later, until the shock goes by. So what this is basically forcing you to imagine is a sequence of events. One is where you have the CME, you see the CME in a coronagraph, and then shortly thereafter, you see, this is my only picture, by the way, of SEPs. It's an actual picture. It's the noise. It's this snow on the detector. Those are the high energy particles. Those are these guys right here, these quick arriving, very high energy particles that are causing problems on your CCD detector. And so you see these particles and then it sort of dissipates away. But several days later, or a day, depending on how fast the CME is, you see the actual shock wave here, and the CME arrives a little bit later. This is the CME flux rope. This is the shock driven by the CME, which actually accelerates the particles. And so it's the shock that actually accelerates the particles, not the actual CME itself. Okay, so that's my background. I'm due to end in 10 minutes. Is that correct?
10 minutes, yeah.
Yeah. Let me just kind of rush through some of this stuff quickly here. I kind of figured I would just go through background, and that's totally fine. But let me just say, from the sort of theory quantitative aspect of this problem, energetic particles are really treated as test particles. That's okay. If anybody attended the Helio 2050 conference, I gave my view for the future was that we stop treating them as test particles, because in many instances you have to, they contain a lot of energy. Now, on the one hand, they might influence the plasma in fields through the momentum equation, but I think more important is that they're part of the energy budget. So they extract their energy from the fluids and plasma, but then they're mobile and they can go to other places of the system, and you have to follow that energy. But they have traditionally been treated as test particles. And so that's the way the theory has been developed, and the way Parker did it a long time ago, and others. He wasn't the only one. They're also assumed to not interact with each other. Okay, so there's no particle-particle collisions. In fact, the energetic particles probably only exist because it's a very tenuous plasma. If there was a lot of collisions, you wouldn't have high energy particles. So it's really just the Lorentz force. The Lorentz force determines their motion. You need to know what the electric and magnetic fields are. You can get them from MHD simulations, for example, but this is not simple. Okay, you might think, well, somebody runs an MHD simulation of a coronal mass ejection. Let me just put particles into that. But unfortunately, the energetic particles have their own characteristic length scales that has to be resolved, and they're not necessarily compatible with MHD simulations, and so there could be a mismatch in scales there. So it's not as trivial as it might just sort of seem to do that. Very common to do this using what is called a kinematic model, where you define the electric and magnetic fields yourself. And it's often easier to do that. I mean, I think in some sense, dynamo theory is kind of like that. You sort of define the flow pattern that you need to generate a magnetic field. But ideally, you'd like to do it fully self-consistent. But this is a very common thing to do, is to come up with a kinematic model. Again, you have to sort of go back and look to see how realistic they are. Perhaps the most useful thing that has been done through the years is you average over an ensemble of particles. So while it's interesting to see what one particle might do, in electric and magnetic fields, you can sort of fool yourself by extrapolating too much from a single particle orbit. So it's best to imagine an ensemble of these particles, and there you can arrive some very useful equations by sort of massaging the initial, basically Lorentz force. And one of them is known as the Parker equation. That's perhaps the most famous one. And then there's the focus transport equation, which with these references here, I won't go into it. It's basically allowing for anisotropies, so you retain pitch angle information. There's basically four main transport effects of energetic particles that describe their behavior. One is diffusion. So yes, energetic particles execute essentially something like a random walk, but they do it not by bouncing off of each other, but by basically through resonant interactions with turbulent magnetic fields. It's basically wiggles in the magnetic field that cause resonances that basically mimic diffusion. Then there's also convection with the plasma, because when they scatter, they do so in a frame that's moving with the plasma. Then there's drift motions. If anybody's done any orbit theory, one of the first things is something known as guiding center drifts, the guiding center theory. These drifts play an important role. There's drifts due to the gradient of the magnetic field or curvatures in the magnetic field, the electric field drift, which I mentioned a little bit before. And then there's energy change, which primarily comes about through expansion and compression of the background fluid, in this case, which is the plasma. And a shock wave is a very good example. It's a very large plasma compression because it's so thin, and that leads to acceleration. All of these effects are important. It's hard to sort of isolate these effects. With the case of a shock, you can see a shock wave go by and you can see energetic particles and you can say, oh, that's the energy change term. But often, especially with cosmic ray transport, it's not so simple to separate out the effects. They were all combined in Parker's. So this is his sort of famous equation that he wrote in 1965. I basically don't want to talk too much about it, but this is basically F is the distribution function of cosmic rays. This is the solar wind velocity or the plasma velocity, depending on what your application is. So this is advection term. This is the diffusion term. It looks like a diffusion term. Drifts and energy change and the source. The drift velocity that appears here actually has this explicit form. This was actually derived by a paper by Phil Eisenberg and Randy Giacalone, basically showed, and this follows directly from the Lorentz force acting on charged particles. The diffusion tensor actually has components parallel and perpendicular to the field. This can also be derived. Let me skip over the cosmic ray transport stuff real quickly. Here I derived the 22-year cycle, but since I'm sort of low on time right now, I just kind of want to go through this really quickly. So this is the Lorentz force, which we're all used to. I prefer Gaussian units, by the way. If you're using SI units, that C is not there, okay, in the second term on the right. If you solve this for a constant magnetic field with no electric field, you just get gyration around the magnetic field, just helical orbit. If you have a constant electric field that's applied, but don't allow the electric field to be parallel to B, so I'm only considering ideal MHD electric fields, then what arises is the gyro motion plus a drift term. Okay, so the drift term is given there in the right. And I'm going through this quickly, by the way. You could go through this at your leisure, and hopefully some of this is familiar to you all. But of course, constant fields are not what we see in the solar system. So we have to allow the field to fluctuate. But then there's a couple of limits. On one limit is when the scale of variation is very large compared to the gyro radius of the particles. In that case, you can do something known as guiding center theory, and you come up with these equations. Okay, this is in actually the textbook chapter for this summer school. I really like the textbook of Rossi and Aubert, Introduction to Physics of Space, 1970. It's an old book, but these old books are great. And I think that this is really some of the best orbit theory discussion is in this book by Rossi and Aubert. But anyways, this is where you get the curvature drifts, the gradient drifts, and so on. And this is sort of the general guiding center drift equation. But perhaps more interesting is what happens when the scale of variation, the magnetic fields in space are turbulent on a wide range of scales. And so what happens when that scale of variation is comparable to the gyro radius? In that case, you get basically resonant processes. And in fact, this is an actual orbit calculation. I put in a turbulent magnetic field and I followed the essentially pitch angle. It's the cosine of the pitch angle of the particle. And you can see it was happily moving along in one hemisphere. And then all of a sudden it changed to the other hemisphere. So it went from being in this 0 to 1 hemisphere to the 0 to -1 hemisphere. And so if you're following it in space, it was moving one way. And then all of a sudden it went to move the other way, which is just like a scattering. And so this is essentially a diffusive process. And interestingly enough, by the way, if you plot Z versus X, the position of the particle in X versus Z space, even though it mirrored, it actually followed back its orbit exactly. Okay, well, maybe not totally exactly, but it didn't move across the magnetic field. And this is actually no optical illusion. This is what happens when, and this is sort of a little warning I'm going to give. This is what happens if your magnetic field. So if you're doing a kinematic model, so you define the electric and magnetic fields, but you decide for computational convenience that you want to ignore some spatial, like the magnetic field is a function of say X and Z, but it doesn't, I'm going to ignore the Y dependence. If you do that, then that actually through the, you can just prove this rigorously from the Hamiltonian mechanics of this, that the particles are forced to remain within one gyro radius of the field line on which it starts at forever. Okay, so that's not what happens in space. So you have to be a little bit careful and know your model very well. So I think what I'm going to do at this point is the rest of this is actually going from the single orbit theory to the Parker equation. And if for example, and this is kind of done from the Boltzmann equation, this top equation comes from the Boltzmann equation. The first two, like this term on the left and this first term on the right, if you know what I'm talking about when I bring up the Boltzmann equation, should be familiar to you. The term on the right simply comes from the force that shows up in the Boltzmann equation. And if you do something called quasi-linear theory on it, this term shows up. And it's essentially of the form of pitch angle diffusion. So I noted a single particle that underwent a scattering in pitch angle. But if you consider an ensemble of these particles, then you get something called pitch angle diffusion. It's related to spatial diffusion. This is, again, a spatial diffusion equation. The comparison of these two basically come from these papers and these added notes that I have at the end. And this is how you relate spatial diffusion to pitch angle diffusion. And I think what I'm going to do actually at this point is basically stop at this stage because I'm at the end of the time. And let me just say that I had some added notes at the end of this lecture that go through each of these derivations. I'll say one more thing really quickly. There's another term that shows up in the Parker equation. This is the energy change term. The advection term is pretty straightforward to understand. It's just simply because the scattering centers when the particles scatter off these magnetic fields, the magnetic field is frozen into the plasma. So in the plasma frame of reference is where the scattering conserves energy. So this manifests itself as an advection term. But there's also an energy change term. The energy change term doesn't involve the electric field. You'll see there's no electric field here, but it's there because, again, going back to the Lorentz force, you can derive this, and that's sort of what's summarized in these equations here, and in my notes. Okay, my notes go through this, and you may notice that my notes are a little shaky because what I did was I gave the lecture in real time onto transparency. So, but the notes contain the details of those derivations. So, I think I'll stop there because it's my time.
Okay, thank you, Joe. I don't know if someone has just asked if you have a minute here. Is
Of
there an
course, yeah.
integrated flux comparison with the inclusion of far side energetic particles from the stereo spacecraft?
Okay, can you repeat that question, please?
Is there an integrated flux comparison with the inclusion of far side energetic particles from the stereo spacecraft? So,
Okay,
what,
so
yeah.
please speak up if I'm answering this, if I'm misunderstanding the question. But I guess the way I'm taking this, and let me go back, and maybe I'm wrong, but maybe Dana, if you think I'm not interpreting this correct, let's go back to.
Brian should interrupt you.
No, let's go back to this. I think maybe I'm wrong, but I believe it's whether or not that because we have stereo, and unfortunately stereo is moving though, so it's not always like on the far side. But it's a question of whether or not this integrated thing there's a dependence on, maybe it's just because we happen to be at Earth. Like what happens if we have planet Vulcan on, the other, isn't Vulcan the anti-Earth on the other side of the sun?
I believe that's Nemesis.
Okay, right. Okay, sorry, right. The Earth on the other side. So if we have an Earth on the other side of the sun, would these be the same? That is actually an excellent question. I can only say that because this total sum is dominated by these very large events, that there could very well be very large events that occur on the back side. Say during solar cycle 24, for example, maybe there were some very large events that we just missed because they were on the back side of the sun. So it's actually an excellent question. Does this translate to it as a mutual dependence? Yeah, so that might be a good motivation for putting a spacecraft at L5, for example.
Yeah, I think you answered the question. Brian has said, yeah, that was the question he wanted. Okay. I know you have to leave very soon.
No, I can stick around for a few minutes. I told him to expect me 20 minutes late. So.
Okay. All right. And I believe we're going to, we usually just go right into office hours.
Oh yeah. Yeah. Sorry about that. Yeah.
No. You can be part of this office hour as well.
Okay.
Ben has rejoined us, so he's ready to answer any questions about the solar wind.
Okay. Well, I'm going to stop share then if I don't have more slides.
Yeah.
So, anyways, thank you all. I think I'm gonna run off to this other meeting I have, but thank you all for listening, and please, I'll be around tomorrow. I think it's about this time. I think my office hours are yeah. So I'll be here for a half hour, and I can, stay a little, whatever. I'm totally flexible. So feel free to, to ask questions or anything, and go over those notes. If you have any questions about my notes, if you can't read my handwriting, please let me know.
Okay.
And I'll be posting the slides from this lecture as well shortly.
Okay.
Thank you, Joe.
Thank you all.
We'll see you tomorrow.
Okay. See you tomorrow.
And Ben, welcome back.
And just before people log off, there's no specific time zone group work for tonight, but David Brain has asked you to review chapter 12, and his comment was you don't need to do a close reading, but you should at least be familiar with the topics that are covered in chapter 12 from the heliophysics principles, and maybe some of the conclusions as well. So familiarity with the topic is all David is asking for tomorrow. So other than that, I'll turn it back over to Ben for follow-up questions from his lecture, and we'll, if you leave, we'll see you tomorrow.
Yeah, if anyone has any questions, either about what I talked about today, or just more generally about the topic, feel free to go ahead and ask.
Well, I'm going to take the opportunity to launch a question. So according to if I gathered what you were saying, if somehow the Alfvén wave flux from the solar chromosphere, low corona, whatever, were to increase dramatically, the solar wind speed would basically track it, right? I mean, that's what's fixing our solar wind speed, is just that flux of Alfvén waves.
That's what's fixing the mass loss rate. So the mass
loss rate.
The M dot will scale to a good approximation with that Alfvén wave flux linearly. And because of that, actually, if you think about other scalings, the velocity of the convective motions is basically fixed. It's fixed by the radiative luminosity. And the magnetic field strength, the open magnetic field strength that connects out to the interplanetary medium, that can vary from cycle to cycle. And the total Alfvén wave power scales roughly like the square of the convective velocity at the sun times the density at the sun times the Alfvén speed at the sun. And so there's a proportionality to the overall magnetic field strength. So one place that this proportionality shows up pretty well in the data is that the mass loss rate is kind of linearly proportional to the strength of the unsigned magnetic flux, open magnetic flux. And that's consistent with this model. So yes, if that Alfvén wave power goes up either through the strength of the background field, or if somehow we could turn up the rate of convection, yes. Like, so for example, if you were to scan across different stars at different spectral classes of stars, you would have different values of the velocity of those convective motions. And if you could actually measure that, which we unfortunately cannot directly, but if you could, the prediction of this model would be that the mass loss rate would scale. Actually, it's interesting. For fixed magnetic field strength, it would scale quadratically with delta V. Of course, the magnetic field strength itself is determined, to leading order by an equipartition with the kinetic energy. And so you might expect more of a delta V cubed dependence there. And actually delta V cubed is kind of like the overall luminosity of the sun. So there are some scalings that could be worked out related to this model, which I haven't really explored in detail, but but definitely what you were saying before, that the proportionality to the Alfvén wave power is there, and particularly with the mass flux. And also in this model, again, at the back of the envelope level, the outflow velocity is going to be the escape speed of the sun. And that's fair, like at the back of the envelope level, that's always true for the solar wind, 300 to 800 kind of brackets, the 600 kilometer a second escape velocity. There is another regime though. If you really dial down the speed of the convection, because the mass loss rate goes way, way down, you end up interestingly getting to a regime where there's so little mass that's expelled in the wind that you don't lose much energy to that PDV work. The expansion is no longer the main sink of internal energy in the subalphanic region of the solar wind. Instead, it's the conductive losses back to the sun. And in that regime, what happens is that the M dot goes down dramatically and the outflow speed goes up dramatically. So interestingly, there's a kind of anti-correlation between the speed of the convective motions and the speed of the wind. So that's kind of an unexpected outcome of the model.
Actually, though, when you mentioned the dependence on the flux, I'm thinking of that early phase when the sun was spinning much faster. It's spinning down.
Yes.
And then at least the Rossby number is much lower, so presumably the dynamo was much stronger, and we get higher open flux. So I would think higher mass loss. And I think that is a standard picture. As you're getting that mass loss, you're losing angular momentum, and therefore you're spinning down. Is that?
I think that's right. And actually, I think the scalings of this model could probably be fruitfully applied to revisit some of those standard pictures. There may be differences in there, and I haven't done that, and it's not really a major direction for me at the moment, but it's something that certainly will be kind of low-hanging fruit for someone with the interest to do it. At some point, I'm sure it will be done. The other thing that's kind of interesting to me about the model is that if you think about, like, so one of the sort of hopes for the solar wind physics, if you think about it from a broader scientific perspective, is that the sun and the solar wind could be a prototype model for the outflows driven by kind of any system with the following properties: that you have some dense object at the center, and it's surrounded by lower density magnetized plasma. And the dense object has something which is shaking it or roiling it. And if you think about that sort of general description, it applies to a lot of different systems. So certainly stars with convective zones extending to their surfaces or just below their surfaces. But also if you think about accretion flows around black holes, so some of those accretion flows are very tenuous, but some of the most luminous ones are actually dense plasma that's geometrically thin but optically thick, and it orbits in a disk around some, say, black hole, and the mechanism by which the plasma loses angular momentum and gradually falls in is turbulence. And so if you thread that accretion disk with a magnetic field that goes above and below it, the turbulent motions in the disk can launch waves, Alfvén waves, out along the magnetic field lines, just like the convective motions on the sun do for the corona and solar wind. And a similar process could occur there. Similar physics can also occur if you think about the end stage of a supernova, so of a massive star. A massive star, once it's done burning through the useful nuclear fuel in the core, and it has converted that core to iron. And if you have a star with, say, 10 or more solar masses, that you will end up with like a 1 or more solar mass core of iron that's just inert at the core of the star, which can no longer fuse to produce energy, because iron is sort of at the minimum of the binding energy per nucleon for all the elements, or well, maximum in terms of the magnitude of that binding energy. And so the iron can't produce any more fuel, and if the core gets too big, it collapses, and you can form a neutron star. And then or if the star is big enough, you can form a black hole. But if you form a neutron star, just when it's born, the neutron star is also turbulent, and it's also connected by magnetic field lines out to the envelope of the neutron star. And there are models, I think there's one by Brian Metzger and Elliot Quattert and colleagues, where motions on that proto-neutron star, just born neutron star, can launch waves out along magnetic field lines and heat the envelope. And so in principle, this could be relevant to interesting things. Like, would it be relevant to supernovae? I don't know, but possibly the heating of supernova remnants. Oh, is there a question?
Yes, we have a question. Can you see the chat?
I can. I have a basic question. The mechanism for the acceleration of CME is the same as the solar wind? No. So in the case of the solar wind, so here's one way to think about the solar wind is just the simplest way to think about the bulk of the solar wind is that you have what are called coronal holes, which are open magnetic field lines that connect the solar surface out to the interplanetary medium. And the background structure is kind of fixed, and then you have this like turbulent motion at the base, which launches these waves out through the coronal holes. And it is that sort of wave energy flux that drives the outflow. For a coronal mass ejection, you start with a closed magnetic structure, which is building up potential sort of additional magnetic energy over time that's eventually suddenly released. So you go from a closed structure that maybe, and the exact mechanism by which this happens is still debated, but something can happen where maybe reconnection is triggered. You can somehow lose the equilibrium that you start with in this sort of magnetic arcade, which then releases this energy suddenly and generates this rapid outflow. from that's very rapid, very low down. It's not driven by a wave energy flux, but more by that stored magnetic potential energy. It's not really potential energy, it's stored magnetic energy in that initial magnetic configuration. And so you can get flows that are, hundreds, even 1,000 kilometers a second, really close to the sun from that process. The solar wind will gradually accelerate to 300 to 800 kilometers a second over 10 to 20 to 30 solar radii from the sun. That's a good question. It is different physics. I have respect for our Indian colleagues. If at least Neelam says that you are from India, it must be very late there. Past midnight, I imagine.
Oh yeah.
We have participants getting up in Hawaii early in the morning, and we have our Indian colleagues who are staying with us late at night. So yes, it's a challenge on both ends. Hey Ben, I have a question for perhaps a future discussion between the two of us. When I go to understand something, I find that my approach to trying to understand something is I write a little some computer code, especially if it involves doing an integral and doing a numerical integral or something like that. So I worked my way through Parker's paper, one of Parker's papers. Now I got to remember which one. It's in the comments in my code.
Yeah.
And by programming it up and recreating the classic diagram that shows going through the solar breeze and the solar I forget what the other ones are, but the nozzle, the sweet spot, as it were. And so one of the things I often look for is ways to turn these sort of things into places where students can explore something. And I sort of there's a few like knobs and twiddly things that can be played with, but I got stuck and I wasn't sure what to twiddle with.
In terms of the Parker model?
In terms of the Parker model, or maybe going one or two steps beyond it.
Yeah. I can certainly address that question with regard to the model I was just presenting today, which has some interesting knobs to turn.
Yeah.
On it. And actually, one thing I was actually interested in maybe talking to you about sometime. I have a code which solves the more complicated equations of my model in Python, and it's a kind of thing that I imagine students might be able to use in this school potentially to explore. It's a quick way to get solution. Like you can actually get a whole profile for the solar wind. I showed one of those diagrams that you were describing. Also, it can be, but anyway, that maybe is more detail. But
sure, okay,
that is something that where there's a lot that goes into it. In fact. The part that was in the paper that I published, the solutions were all for a fairly simple magnetic field profile. But another thing that you can do with this model is solve the equations for a more like global magnetic field profile. For example, there's a paper by Cranmer and Van Balahoyen in 2007, where they solved their Alfvén wave-driven solar wind model in what's called the Benaskiewicz global solar model, which is like a sort of global dipolar type model for the magnetic field of the sun with a current sheet. And you can do the same thing with the model I developed. And it's not in the paper, but you can solve the equations for that. And there are some other free parameters you can vary in this. In terms of the Parker model, there's a really nice paper by Durney in 1970 or 1971, where he solves the equations of the Parker model. And the way he does it is he first does a similarity transform to change variables So that instead of density and temperature and flow speed, he has some combination, like dimensionless combinations of those variables. And he solves the equations in those variables, but then from that one solution, he can then get back a whole family of solutions which illustrate how the flow speed that you would see at Earth depends upon the input density and the input temperature at the coronal base. So that's something where there would be some nice, you know, and actually there's more than one way to solve those equations. It might, you know, you could also solve them case by case, keeping the primitive variables, density, temperature, flow speed. And that would be another way for students to, you know, build it up step by step. You know, so that those are really the only kind of knobs in the Parker model, those kind of inner boundaries of density and temperature.
Right. Okay. All right. Well, maybe we can find some time later on in the summer to brainstorm some other ideas. That sounds
I'll
like
say, you know, having played around with these equations myself, there's also the adiabatic index. If you don't do it isothermally.
Absolutely, that's actually a good point. Which yes, and sort of reducing gamma from the physical 5/3 towards 1 was the traditional way of mocking up a heating function. Right. That's absolutely right. So that would be another neat way to, you know, twiddle them. I was restricting myself to physical variations of this system.
Yeah. You know, the crazy thing when you do that is you find out if it is 5/3, I don't think there's any way you can get a wind. It's like it ends up not crossing a sonic point, or I've forgotten the real pathologies that come from that. So you need it to be lower than 5/3.
Yes.
And of course, 1 is isothermal. And so anywhere between those, you'll get something.
Yeah. So yeah, if you take out the conduction and make it, if you take out the conduction and you put in gamma 5/3, the critical point goes to 0. And so you like it exists, but you know, in the limiting sense, but that's a weird case. But when you put the conduction in, then and you keep the gamma of 5/3, then you get all of these other solutions like that Durney was looking at, where the flow speed at large distance depends upon the density and temperature at the coronal base. But yeah, that would be another. In some ways, that's one nice thing about what you're describing, is that you can actually do that problem analytically to get the mass loss rate, and then you could solve a Bernoulli's equation simply to get the flow speed at any point. So that, in terms of like developing something for students to do at this school, that would be a great starting point. Then putting in production would be one level higher in sophistication. And then the paper I just published that I was describing in today's lecture, that would be a much, much more complex, because there's a lot more physics that go into it. The code is, I think it's something, you know, there's a longer code. You know, the code that I have has a lot of different diagnostics, which makes it more than 1,000 lines. But the real core of it wouldn't have to be that long. You could, but I have, that includes every plotting routine that I used for every different plot of the paper and stuff. But it's still, even in its pared down form, it will be a lot longer than just a simple Parker type solar wind.
Okay, cool.
I think I scared off all the students, except for maybe two.
Unless they're asleep.
They have good excuse to be asleep if it's 1:30 or something for them. But well, we could also call it, I guess.
So yeah, up.
You're very welcome. And if you have any other questions, do feel free to ask them.